All right, hi everybody, Mr. Wiggins here. In this episode, we're going to talk about electric fields and electric field lines. We'll also talk about a little bit of review since I know it's been a while since we've been in class together and since we started this unit. So for this episode, talking about electric fields, we're going to define an electric field, talk about electric field intensity, look at a couple technologies which we've discussed before in class, and then also if you go through some of the PowerPoints, there's some fairly simple calculations using the equations in the coming slides. All right, so just as a review, electric fields are almost everywhere in today's day and age in nature and in technology. Basically, an electric field is what causes any electric force. All right, so an electric field, just in point form, is a force that exists in a region of space around a charged object. It's really important to remember that it's a vector quantity, so it has direction, and it can exert an attractive or repulsive force on other objects based on if they have like or unlike charges. So we'll look at a little example here. So here we have positive charge of some kind, and for the sake of this diagram, this Q here, we talked about a charge being described by the letter Q. It's also going to be a positive charge, so they're going to repulse each other. And that's why we draw this little vector line with a force electric away from the center charge, because they are repulsing each other. If this Q was a negative charge, like an electron, it would be attracted to that positive charge. The other thing to note in this diagram is that it's shaded, and the closer shading towards the middle means that the electric field strength is stronger the closer you get. That means the closer that this positive charge gets to the other positive charge, the more repulsive effect there's going to be. And vice versa, if we had a negative charge here, the closer we got, the more it would be attracted to that positive charge. Okay, so we're going to talk more about this in electric field lines, but just as common notation, there's two ways to look at this. When we're drawing electric fields, if we have a positive charge, the vectors are always going to push away, or the lines are going to push away from that positive charge. So you can see here the arrows are pushing away. And if you have a negative charge, the arrows are going to come towards it. And that's just common notation when we talk about fields and forces. Alrighty, so we're going to move into the math. And like I said, the equations aren't too tricky. It's just remembering in your calculator how to use powers of 10, because we're working with really big numbers and really small numbers. If we're looking at like electrons and stuff like that in their mass, those are really small numbers. So here we have this backwards 3. It's an epsilon symbol. It is the electric field intensity that we're going to be measuring. We have K, that's just a constant, Coulomb's constant, which we talked about before. We have Q here, which is a measure of the charge in coulombs. Radius would be the distance between 2 points, and it's measured in meters always. And then here we have the force electric, so if it's force, it's in newtons. And then here again Q. So we can rearrange this equation to solve a number of different problems, and it's fairly simple solving compared to some of the other things we've done together. What's more complicated is when you start thinking about how these charges interact with each other, or how these vectors will interact with a charge in a given point. So we're going to look at a couple examples of that. So here we have two positive charges. So these positive charges are interacting with, let's say, this point in space. We're going to call this also a positive charge. So what's happening is there would be a straight line up from here and a straight line from here, and that would give you this direction here, your electric energy, your net here, if we added up the x and the y's of both the charges. The reason they're drawn, electric fields are drawn in a curved manner like this is they're supposed to represent any point in space and how that charge in space would be affected by these charges. So, for example, if we pick another point in space, if we pick, let's say, this arrow here, we would have a straight arrow from here pushing this down this way, and we'd also have an arrow pushing it this way, so we can make a smooth line along any of the like vectors, and that's what these curved lines develop from. And again, we'll talk a little bit more about that when we talk about electric field lines. So some different examples of electric fields: X-ray machines, LCD displays, telephone, particle accelerators are all like technological examples. Lots of different organisms also use electric fields, like sharks use them. And then one of the things we looked at in class, which is pretty cool, is an instrument called the theremin. If you are interested in any more of these, there is more information in the full discussions that I've posted, or you can just look up them on your own. So now we're going to move on to electric field lines, now that we know what an electric field is. And we already discussed a little bit about the lines in the last section. But we're going to look at different electric field lines. We're going to look at if we have a negative charge and a positive charge, so that's a dipole. We're going to look at uniform electric fields, something called parallel plates, and different examples following that. Okay. So like we said just a little bit earlier, the one thing we need to remember is that positive charges, the electric field lines always point away from the charge, and negative always point towards that charge. If you want, you can kind of think about this like gravity, in the sense that gravity, we associated a negative number, negative 9.81 meters per second squared, and it pulled down. So we're kind of saying that the negative charges pull towards the atom, or not the atom, but the object, the charged object. All right, so dipoles. So dipoles, I like to think of chemistry, some background. So we're going to think of 2 points, but with equal and opposite charges, and they're going to be separated by some distance, and we call that R. Like normal in physics, we always label our distances with some letter, usually D or R. And this is called an electric dipole because we have a positive and a negative. So they're going to be attracted to each other, these 2 charges, but they're also going to have some electric field lines. So if we were to draw the electric field lines for the negative, we point again towards the arrow, and the positive point away from the arrow. One thing to note is if you have, the more lines you have on a charge, that means the charge is stronger. So if this charge, let's say this negative charge, was half as strong as the charge drawn, maybe we'd only draw 4 lines because there's 8 here. And if it was twice as strong, we might draw 16 lines. All right, so right now we have the charges are isolated from each other. We have this line in between. So now, if we were to connect these charges, we get these weird curved lines. If we want to look, if we want to look at the base lines, we have to look at the end here. So we have the negative going towards and the positive going away. We'll look at a couple different examples to kind of see where these smooth lines come from. For example, if we had, we'll just say this point right here. So this point right here, if we put a positive charge, and we're always going to say, for example, a positive charge, the positive charge Q plus is going to be pushing that charge here straight up. And it's also going to be attracted to the Q charge less strongly. So it's going to be straight up very strongly and then slightly attracted this way. So it's going to have an overall kind of like its overall would be a vector this way. And then if we wanted to look at, so if that particle is moving, if we wanted to look at it over here, it would be attracted more strongly than, like attracted to the negative charge more strongly than it's repulsed by the positive charge. So what these lines are, in essence, is they're like a summation of how a positive particle would be affected by the dipole, or the two particles there. Oh, cut that out. And again, this is a very complex concept because we're trying to describe something with pictures that we can't see, and we're just trying to describe something that's a 3D object in 2D. So I understand if there's a little bit of confusion. All right, we're also going to look at the electric dipole of two positive charges. And again, this is the same concept as before, where we're looking at how would a positive charge, if placed somewhere between these two charges, react, and what direction would it kind of go. So again, we'll do a quick example, except we'll do maybe a bit different example. So if we had a positive charge right here, so it's like kind of equidistant from these two particles, this particle is pushing it this way very strongly, this particle is pushing it this way very strongly. So if you add up the vector quantities, you get this pushing it down. And again, just keeps going down, because if you're here, you have this positive particle, positive object pushing it this way, and this positive charge pushing it this way. And when you add up the vectors, you get, again, an arrow this way. A common analogy might be used, that might be helpful, is if you were to take some like stretchy fabric, and I'm sorry I don't have any, and you stretched it out every way, and you pushed up on that fabric, and you called that a positive charge, and then you placed a marble on the fabric, it would roll away from the center. And the higher you push the fabric, would be like the stronger the charge, and the faster that particle would roll away. Okay, finally, this is where I talked about the number of lines. So here we have two positive, like a charge that's 2 times bigger than the negative charge. So we have double the amount of lines going away from this positive charge. And again, we see how a positive charge would be affected by these two charges at once. All right, the next topic is uniform electric fields. Oftentimes, this is known as parallel plates. Unfortunately, we couldn't do the lab together on this, but I'll try to explain it the best I can. All right, so we have two plates. One has a negative charge, one has a positive charge. And when we draw the lines, what you'll notice is that when the plates are, like anywhere we look, we have a straight line across from one side to the other, except for the very edges where we have this curved line. And again, we notice that the positive always goes to the negative. It's going to become very important later when we start talking about electrical potential difference. All right, so to sum up for parallel plates of charge, and then we'll look at it a little bit more. The charge is always uniform and perpendicular to the plates. So the plates need to be parallel, like in the name, and then the electric field is just perpendicular to the plates. Except near the edges, like we saw, the edges are a little bit of an exception. Except near the edges, the amount of charge on the plates is proportional to the intensity. So intensity is proportional to the charge directly, and the intensity is proportional to the reciprocal of the area. So that means that the bigger the area, the intensity will go down. And then the material between the plates is proportional to the charge. So depending on the material, that's going to obviously affect what your charge is or your intensity. Outside the plates, we have a intensity of 0. So if we just quickly flip back to here, you'll notice there's no intensity here at all. And there's no field here at all. It's only in between the plates. So we can quickly go through a couple practice questions. So we're looking at these two parallel plates. This is kind of an image of something similar to what we would have done in class. So basically, what's the effect when these different things happen? So if we decrease the distance of the plates by half, there's no change to the field. The distance doesn't affect the plates. If we increase the charge on each plate by 3 times, because we have the intensity is proportional to the charge, the intensity will also increase 3 times. And then if we have the area of the plate, since the reciprocal of the area is proportional to the intensity, if we have the area, we'll increase the intensity by 2. So that's everything for electric fields and electric field lines. Again, if you're looking for more information, you can go to the classroom and look through more. I just didn't want to make these videos too long. This is my first one trying with Physics 30, so any feedback is appreciated. Looking to expand and make things a little bit more complicated as we go ahead here with learning at home. And thanks for watching.